Welcome everybody to today's seminar, and yeah, it is a little later than usual, so it's great to see at least a few people joining today. Uh, let's welcome Fabian Ruehle to give his talk on machine learning for theoretical and mathematical physics. He has received 2 degrees in physics and computer science from the University of Heidelberg in Germany. He completed his PhD in theoretical physics at the University of Bonn under the supervision of Professor Hans Niels. After postdoctoral research positions at Daisy Hemberg, the University of Oxford, and CERN, Fabian joined Northeastern University in Boston in 2021, where he is now an assistant professor. He's also a senior investigator at the of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions, which is a collaborative institute for AI and physics for the Boston-based universities, Harvard, MIT, Northeastern, and Tufts. We thank you for sparing time out of your schedule for us, and over to you.
All right. Yeah. Thank you very much for the invitation and for the kind introduction. Yeah, so I want to talk a bit about research that I've been doing essentially over the past 7 or 8 years. And essentially the question that I have been asking is how can we use machine learning and apply it to areas like theoretical physics or mathematical physics or even pure mathematics. And the talk is based on mostly this paper here. It's a paper that appeared last year in Nature Reviews. So we're reviewing all of the techniques that I want to talk about today. And this paper was written with Sergei Gukov at Caltech and Jim Halverson, who is a colleague here at Northeastern. And the 2 examples that I'm giving are based on these 2 papers. So you can look here if you want to see more details. One was written mostly with colleagues from IFI, mostly MIT, some at Caltech, and this paper, which was written with their colleagues here at Northeastern. Okay. So in some sense, formal areas like mathematics or theoretical physics have been late adopters of machine learning, and there are good reasons for why that is. So other disciplines like, I don't know, astrophysics or cosmology or biology have used them, or even particle physics have used these techniques much, much longer than we have. And the reasons for that is that neural networks are not really suited the way they are used in these other disciplines. It's not really suited for what we want, because they are black boxes, meaning they can do amazing things, but you have no idea how they do it. So it's notoriously difficult to interpret what a neural network does. They are stochastic, meaning sort of the output is probabilistic. It depends on arbitrary choices that you make when you set up the algorithm. These are called hyperparameters, and of course, typically we don't want any arbitrariness in our research. And they're also very error prone. So they do make mistakes. If you ever use ChatGPT, you will have seen it sort of make mistakes or lie to you. And it can be extremely hard to quantify this or to even detect it, to even know that ChatGPT is lying to you. And this poses problems for fields like theoretical physics or mathematical physics, where we want to sort of understand what's going on. We want to interpret the results. And especially in mathematics, we need provably correct results. So we don't want just even to be able to quantify the error. We need the error to be exactly 0. And this is not what sort of machine learning, out of the box machine learning techniques typically do for you. So I've been thinking about ways in which we can sort of change this or adapt the algorithms that are around in order to sort of address these challenges here and get to something that's understandable, interpretable, and can lead to provably correct results. And there are many avenues you can sort of pursue in order to do this. In this talk, I want to talk about 2. One is you change the neural network architecture. If the neural network architecture leads to it being black box and uninterpretable, the idea is to come up with a different neural network which sort of does not suffer from this. And there are a few things that make neural networks very, very difficult to interpret. One is it just has too many parameters. If you look at ChatGPT, there's 1 trillion parameters. And there's no way that anybody could tell you if you changed parameter 750 million, what would change in the prediction of ChatGPT. So these parameters are very, very difficult to interpret. And even if you look at these parameters, what they are doing is they don't have a single job. So if you look at which neuron in ChatGPT is firing when you ask it to do a certain task, you'll find that the same neuron fires when you, I don't know, translate Hawaiian to Navajo, or you ask it to interpret Beethoven's Ninth Symphony, or you ask it to write a C++ code. So it's sort of the same neuron does many, many different things. So in order for it to be interpretable, it would be nicer if sort of there was a clear separation of the different parts doing different things. And these new networks that we are writing down, these Kolmogorov-Arnold networks, don't suffer from this. And then in addition, they are very nicely combined with symbolic regression, meaning in the end you get out not a stochastic prediction, but you get out a mathematical formula, a symbolic expression that you can then sort of check and interpret and see whether it makes sense as a physical law, let's say. So that's one avenue you can go down. The other avenue is to get a provably correct result, you just give up on interpreting the neural network. And instead, you try to understand what it was doing. So for example, if you try to learn to play chess, you can watch Magnus Carlsen play chess. But then to understand chess, you're not trying to sort of understand how Magnus Carlsen's brain works down to the neuron. And you're not trying to understand the biology of his brain. Rather, you're trying to sort of just look at what he does and then learn how to play good moves and try to understand sort of the tactic and the heuristic that he's applying behind the scenes without asking how he got to make the decision why he's playing this specific move. So that's the second idea. You don't try to understand the neural network, you try to understand what the neural network does. And that is done in a setup that's called reinforcement learning. So these are the two things I want to talk about. I just briefly want to mention a third thing that is gaining a lot of traction recently, and these are automated theorem provers. I won't be talking about this, I don't have enough time, but essentially the idea is you just give a math problem to ChatGPT, and then you train it with standard techniques and with reinforcement learning, and this can now perform at gold medal level at the IMO. So we're getting to a point where this can do non-trivial mathematics. However, this still suffers from the problem that it can be wrong. So this still requires a domain expert, some human mathematician who goes in, looks at the solution that these things wrote and checks whether it's right or wrong. There's another avenue which people have tried, and this is to formalize mathematics in a programming language. And there are many different ways around. One of them is called Lean. So the way you should think about Lean is it's like a programming language that cannot be inconsistent. So as soon as you write a new statement into Lean, it checks whether this new statement is consistent with everything else that is already in your program. So you cannot write quote unquote wrong programs, or at least self-inconsistent programs. And people like Buzzard have used this to formalize the undergrad math curriculum at Imperial. And you might say, okay, sort of undergrad math curriculum, that's all fine. And the Math Olympiad is a nice playing ground, but sort of this is not research level. But this is finding a lot of adoption here. So Terry Tao is formalizing theorems in Lean, including a prime number theorem. And perhaps most prominent is Peter Scholze, who won recently the Fields Medal. And he sort of has this liquid mathematics, and he proposed something that's what's called the liquid tensor experiment, where he used Lean to prove something in this liquid mathematics that he developed. It was a theorem that he wasn't quite sure was correct, and together with the Lean community, he sort of formalized fields level mathematics and used Lean to prove that it's correct. So that's another road you can go down to get something that is provably correct, but as I said, it's not for this talk. This talk I will focus on these two areas on sort of rethinking a neural network architecture, and then on the second part will be on using reinforcement learning to solve problems. Okay, so in order to talk about sort of how we improve neural networks, let me just talk about what a neural network is first. So neural network is essentially just writing down a function in a specific way. So you have, in this case, you have a function which maps from some vector space R2 into some vector space R, let's say. And the way you build this function, or you build this map, is you take your vector in R2 and you apply an affine transformation to it. So you multiply it by Wx plus b, so linear transformation plus a shift. And this W is a matrix. In this example, it would be a 2 by 12 matrix because you're mapping R2 into R12. And then you add a 12-dimensional vector to it. So now this has 2 times 12 plus 12 entries in this matrix and in this vector, and these are called the parameters of the map. So now you have a parameterized linear or parameterized affine map from R2 to R12. And well, it's a map from one vector space to another, but it's a linear, or it's an affine map. So this is not very, very powerful. It can at most sort of do linear things. But of course, sort of in general, maps that you need are much more complicated than just linear in X. So what you then do is once you have your vector in R12, you apply something that's called a unary activation function to it. So you apply to each component of this vector, you apply some nonlinear map. And then you just sort of iterate this. So now I have applied this affine map, some nonlinear map to each of the components. Now I apply another affine map, in this case going into R3. So I multiply by a 12 by 3 matrix, then I apply some nonlinear map, then I multiply by a 3 by 8 matrix, some nonlinear map, 8 times 1 matrix, some nonlinear map. So this is how you build something that's called a deep neural network. It's called deep because you're doing this iteration between affine maps and nonlinearities more than once. Okay, so now I've written down a function which has a bunch of parameters, all the parameters in this matrix W and B. As you dial these parameters, the map will change. And you've written down some sort of parameterized map this way. And now you might say, okay, that's good, but how do I know that I can actually write my problem that I'm trying to solve? I'm trying to learn f of x equals sine x here. This doesn't look anything like the nonlinearity and the map and the nonlinearity and the affine map. So how can I know that the function that I'm actually trying to learn can be written down in this way? And there's a theoretic guarantee that this is always possible. This is what's called the universal approximation theorem. So in fact, you can write any function as a neural network. So in particular, you can write a function you want to learn in terms of a neural network. But unfortunately, you can also write infinitely many functions that you're not interested in. You can also write them as a neural network. So the question then is, if you write down a neural network like this, how do you find the neural network that expresses the function that you're actually trying to learn, and not the infinitely many that it could also learn? That is the problem then. And so neural networks are essentially just function fitters. And this problem is ubiquitous in science or in all sorts of applications. So the most common one is interpolation or regression. So you have a bunch of points and you want to know what function looks like in between. You can also use it for classification. Essentially, what you learn is the decision boundary between the different points. And once you have this boundary, you can sort of use it to say everything to the right is blue and everything to the left is red or so. You can also use it to generate images. So the way this is done nowadays is with something called diffusion models. And what you're learning is sort of, so you're noising an image and then you're learning a map that maps the noised image back to the original image, and you do this in multiple steps, and this is then how you can sort of take noise and generate cat images from it. Or also ChatGPT. So what ChatGPT does is it gets a part of a sentence, and then it's a map from this part of the sentence into the Oxford English Dictionary, let's say. So it has all the words, so all the parts of words at its disposal, and based on what it has seen before, it's predicting which which word from the Oxford English Dictionary you should put there next. Roughly, this is how ChatGPT works. So essentially, when you learn a function, you can do all of these things. And neural networks, as we discussed, can learn any function. So they should be able, in principle, to do all these things. Whether they can do it in practice is then a different problem. And here's what could go wrong. So you could say, okay, if I have 10 points, why do I bother writing down a neural network? 10 points I can just fit with a degree 9 polynomial. A degree 9 polynomial has 10 coefficients, a0 plus a1x plus a2. So that's a quadratic polynomial that has 3 coefficients. So I can fit 3 points by adjusting these 3 coefficients. And that's true. You can do fitting or interpolation using polynomials. However, the problem is if you have a degree n polynomial, sort of the first derivative of this is a degree n-1 polynomial, and the zeros of this thing gives you the extrema. So there are up to n-1 extrema, and that's also what you find in practice. So if you look at essentially these bunch of points here, and I fit this with a degree 10 polynomial, they are in between. There are always these extrema, so maximum, a minimum, a maximum, minimum, minimum, maximum, minimum, and so on. So this is the unique polynomial of degree 10 that fits these randomly chosen points here. And you see it fits these points perfectly. The error is 0. That's how I just constructed this polynomial. However, in between, it goes from 2 to, I don't know, 10 to the 5. So most likely this is not the right answer. Most likely what a human would draw is something like this, not something that goes from here to 10 to the 5 down to 0.1 again. So most likely this is giving you a perfect fit to the points where you knew the answer, but if you now try to ask the neural network or ask this function, this polynomial, what about the value at this point, it will give you an answer that's most likely very, very incorrect. And of course, it's a known problem. And if you talk to people who use polynomials to fit things, so if you took a numerical analysis class, they will tell you never do this precisely for this reason. So what they tell you to do instead is to use something that's called a spline, where you, instead of fitting one huge polynomial, you just fit a bunch of small degree polynomials. So instead of fitting at 1 degree 10 polynomials, you fit 10 degree 3 polynomials or something. So I just put a cubic polynomial that has these 2 points, goes to these 2 points, and then I can use the other parameters to adjust the next connecting spline, which goes from cubic polynomial from here to here. I can adjust it such that it's continuous. The first derivative is continuous. And then I just do this. And now you see, instead of going up to 10 to the 5 here, it stays at order 1. So now it's learned a function that looks like this roughly. And I continued this past 1 here just to see that even if you did this for degree 30 or so, so for 30 points, it will just stay smooth and connect these points. So this is what fitting a single polynomial does versus fitting a cubic spline does. So now what you can also do is you can take a neural network and you can fit it. And the neural network learns a function that's roughly that looks like this for this neural network I chose. I chose a simple neural network, which had depth 2 and a million parameters. And then you get a function that looks like this. So it looks much more like the spline than the polynomial. And you might ask yourself, why is this? So why did the neural network learn this function? And it could have learned, as I said, it can learn any function. It could have learned the degree 10 polynomial that hugely oscillates, but it doesn't. It learned a simple function. And we don't really know why that is. There are many theories around that try to explain why neural network learn these simple functions, why they work so well. But here's at least an empirical observation of what's going on. So if I plot the error on the y-axis and the complexity, meaning the number of parameters roughly of the neural network on the x-axis, what you see is that if I give my neural network too few parameters, if I only give it 5 parameters, it cannot fit these 30 points. It's just not enough parameters to make that work. But then as I start to give it more and more parameters, the error that fits these blue points starts to go down. and then eventually it will reach 0. If it has enough parameters, it can fit perfectly these 30 points. The green curve on here is the error that it has an unseen point. So meaning I just tested what I have to point 0 and 0.1, and then I ask what about 0.05? And assuming that I know what the function is at this point, I can test how far off is the prediction of the neural network or the curve that I fitted with respect to what the actual answer should be. And this is what this green curve is. And you see that initially sort of the green curve tracks the blue curve. So as sort of I'm fitting the blue points better and better, I'm also fitting the points in between better and better. But then at some point I reach a point around here where the parameter count would be optimal. And then if I make my neural network larger or my model larger, then the blue arrow still goes down. So I'm still fitting these points that I'm using to find the function. I'm still fitting these better, but the green arrow goes up again. And this is precisely something that's called overfitting. So what's going on now is it's making the function go through the blue points better and better, which means it's doing worse and worse on the in-between points on this green line. So now it's actually sort of going to something like this, where it's wildly oscillating and not doing very well on the points that I haven't used to fix the parameters. And this has been known for a very long time, and people sort of typically told you sort of do some chi-squared analysis and calculate the optimal number of parameters that you need here, and then use this number and you will sort of get the best result. This is what's called the bias variance trade-off. However, sort of for some applications, this is rather impractical to do. So I don't know how many parameters need to fit the English language or so. It's not a trillion, that I can tell you that, but ChatGPT still has sort of a trillion parameters, and you might ask, so why is that? Why does it do that? Well, the reason is I don't really know where to put this. But now something sort of very surprising happens, and that's what's called the double descent phenomenon. So if I give it too many parameters, the test error goes up and up and up and up. But then at some point, if I just keep it making it larger and larger, the test error doesn't continue to go up. At some point, it turns around and goes down again. And it goes even further down than this point here. That would have been the optimal in the small parameter regime. So it can go down below this. So since I don't know where this point is, what people are doing is they are just vastly over-parameterizing the neural network. They're just giving it a trillion parameters and asking it, okay, so now fit my function. And then it will do so, and it will find a function that sort of generalizes very well, that works very well on the unseen intermediate points. And as we said, we don't know why this is. There are many proposed explanations around for this, but it's a pure observation that it works this way, and this is why people throw that many parameters at problems in neural networks. Okay, so now you can take a step back and look at this and say, okay, so I had these 30 points and I fitted it with 1,000,000 parameters, and the only reason why I did this is to get something that sort of doesn't go too crazy between the points. So you might ask yourself, was that really necessary? Couldn't I have done something like this, where I just put a bunch of cubic splines that doesn't have a ton of parameters and still doesn't sort of give these wild oscillations? And this is precisely the idea that we had for the Kolmogorov-Arnold networks. So instead of using this, where we sort of alternate affine maps and nonlinearities, and we have the universal approximation theorem that tells us that we can write any function in this way, we sort of take a different neural network architectures. So we put the unary functions, instead of sort of acting on the components of the vector, we put the unary functions on the edges here, meaning we apply some function that we express as a cubic spline to each of the inputs. And then at the nodes, we're just summing them all together. So let's say I have two inputs. I would transform it with one cubic spline. I would transform the second input with a second cubic spline. I would just sum them together. And I can do this in three different ways with 3 different cubic splines. And then I just take these, I transform them again, and I sum them together. This is This is what Kolmogorov-Arnold networks do. And then you might look at this again and say, okay, well, how do I know that I can actually write my function as a cubic spline in the sum? But in mathematics, there's something that's called the Kolmogorov-Arnold representation theorem. And that tells you again that you can write any function in this way. So you can write any function in terms of just sums and unary functions. So essentially, we are learning too many functions, and even in school, when you learn multiplication, so we don't even need that. You can write everything as just sort of as a sum of unary functions. So the plus is the only non-unary function you need in life. That is what the Kolmogorov-Arnold theorem tells you. So let's look at this in practice. So let's say I have data that follows this formula, exponential of sine of x1 squared plus x2 squared plus the sine of x3 squared and x4 squared. Okay, I take my inputs x1, x2, x3, x4, and I somehow transform them, and I get the output. And now I'm training this can, meaning I'm adjusting the cubic splines until the output matches the output of this function. And let me pretend I don't know what this function is. I somehow want to find out what this function is. So I can train it, and as you see, sort of as the training goes on, it's fixing the cubic splines to look something like this. Now the error is very small, so we can stop the training. But the advantage is now we can look at this and we can interpret it. So we see that what it does here is it takes x1 and it applies a parabola to it. So it's taking essentially x1 squared here. And it takes x2 and it squares it. And then remember, at these nodes, it's just summing it up. So at this point now, what I have is I have transformed x1 and x2 into x1 squared plus x2 squared. Likewise, I have x3, apply a parabola, x4, apply a parabola. So at this point, I have x3 squared plus x4 squared. Then I look at this is a sine. So now I'm taking the sine of x1 squared and x2 squared. I'm taking the sine of x3 squared and x4 squared. I sum up the sines, and then I take an exponential. And that's the output. So now I can just look at this and get the symbolic formula that I used to sort of generate my points. I can just get this from looking at the computational graph of the can and seeing what it actually does. And once I have this formula, this will, of course, be completely exact. It will not sort of have any extrapolation errors. And I might be able to interpret why. So why does it depend on x squared? Why does it depend on the sign here? So now that might lead me to sort of postulate new physics laws or new laws behind whatever map it learned here. And you cannot do this with a neural network. So that's one way in which cans are very helpful for this symbolic regression task. The second thing where they are very good is what's called the neural scaling laws. So let's say you have a neural network and it performs with some error, so with some accuracy. And now you ask yourself, how can I make this better? And typically there are three ways you can make your neural network better. One is you just train it for longer. One is you make the neural network larger, meaning you give it more parameters. And the third way is you give it more training data, so you give it more sample. And again, this is an empirical observation. There are different explanations around for why this is, but not universally agreed upon as far as I know. People observe that if I keep two of these things fixed and I change the third one, so let's say I keep my training time and my sample size fixed, and I change the number of parameters in my neural network, the error goes down with a power law. So n to the minus alpha, where n is the number of parameters. And the same is true for the training time. If I keep the other two fixed, it's also power law. And the training sample size also follows the power law with different with different exponents here, but it's always sort of this power law behavior. So you might ask, okay, so somehow I want this alpha to be as small as possible so that the error goes down as quickly as possible. And now you might ask, what sets the scale alpha? And Kaplan and Sharma sort of suggested that this alpha is governed by the intrinsic dimensionality of the data manifold, whatever that means. So essentially meaning if you have a collection of, let's say, natural languages of sentences, or I have a bunch of cat images, you can ask, what is the dimension of the manifold inside pixel space on which all cat images lie? Or what is the dimension of all English sentences within sort of a word cloud of all gibberish I could possibly write down in the English alphabet. In some cases, this is not really mathematically well defined because, well, if I have a cat image and I change a pixel, certainly it's still a cat image. But sort of it's a rough idea, and for mathematical applications, the input manifold is very well defined. So you can answer what is the question, what is this dimensionality? And in the case of neural networks, it was suggested that the error goes something like 1 over d. And there's something that's known as the curse of dimensionality, because if your input manifold is very, very big, let's say it's 1,000, then this alpha is 1 over 1,000, so alpha is very small, so your error goes down very, very slowly. You need many, many, many more parameters in your neural network to get your error down. And that is the problem. And typically, the intrinsic dimensionality of your data manifold is nothing that you have control over. This is something that is sort of given to you by the problem, by the physics problem you're trying to solve. So for cans, this alpha actually does not depend on the intrinsic dimensionality of the data manifold. Sometimes cans don't see the dimensionality of the data manifold because it's just unary function. So it only always ever sees a single input. It doesn't see the entirety of inputs. And in this case, this alpha is just given by the degree of the polynomial of the spline plus 1. So for cubic spline, this alpha would just be 4. So your error would always go down with like a n to the minus 4. And
Professor Fabian, there
yes.
is a question. The
Yes,
question
please.
is, you explain how the motivation, like one of the motivations behind cans is that we are trying to avoid that double descent phenomena that we saw because we do not have any concrete explanations for it, right? So
Sorry.
my question,
Yeah. So what I meant is we're not trying to avoid it. So so that we don't have to go there because I mean there's nothing wrong with doing double descent, but so what it does, it costs you 1 trillion parameters to go here, where which makes it very, very costly to train this neural network that is that large. So training ChatGPT costs millions of dollars. So if you somehow don't have to go here, if you can do something that has much, much fewer parameters, but still does not oscillate in between, that's nice from a computational point of view, but also if you have fewer parameters, the neural network is, or the model is easier to interpret.
okay. So like we can interpret the neural network for fewer parameters.
Yes, it's exactly. If the fewer parameters it has, the more chance you have of saying, okay, if I actually change this one parameter, my function reacts to it in this specific way.
So isn't that like a human constraint on it as opposed to like a mathematical constraint on it? If like I include more parameters, then the same methods which allow me to interpret it using less parameters, I should be able to interpolate that to more parameters, right? Or am I missing something?
So yes, so the fact that humans can only interpret a specific amount of parameters is a human constraint. So sort of if you want to look at your neural network and say what it does, you might be able to do it for something that looks like this. You might be able to say, okay, so if I change the parameter that goes in here, this will change sort of how strongly sort of the things that come out of this are affected, and then you might be able to follow this. But it's quite complicated. And as soon as you have 1 trillion here, or even like even with 1 million, it's completely hopeless to say, okay, so if I change the parameter that controls sort of the affine map that goes from this input to this specific node, it's possible to see what that actually does.
And can avoid this by using fewer parameters, right?
Exactly. Can avoid this in different way, in many ways. So one way is it has much, much fewer parameters. So instead of having this 12-dimensional layer here, I just have this I just have a spline that goes into sort of this 3-dimensional layer here. So I can just look at these functions rather than sort of building building out this function using, you know, huge affine maps and nonlinearities and maps into 1,000-dimensional vector spaces. I'm just operating on unary functions, so I can just look at the graph of the function instead of looking into something, so trying to picture a map into a million-dimensional vector space. I'm just looking at a bunch of maps from R to R essentially here. And these I can plot and look at them and understand what's going on.
Thank you.
Excuse me. Wouldn't you
Yeah.
be learning the parameters of each cubic spline here as well?
Yes, you're learning. Yes, good. Exactly. You're learning the cubic spline. This is what you're doing in order to train and can you're changing the you're
So
changing the
does it then,
parameters.
so how does it then reduce the over parameterization problem? Because what I'm trying to understand, you've replaced your sigmoid or your tan hyperbolic, which introduced the notion of probability and non-linearity, right, in all of your layers, right? And you've replaced them with these cubic splines, and then you've added those up, right? And
Yes, exactly.
then right. So how does the parameterization problem change here? Because is it just the fact that you can just look at the map, like the function, and you don't have to basically interpret? It's much more interpretable, right? Because you don't have to look at A, B, and C and all whatsoever parameters, right? Is that because of that?
Yes, that's one thing of saying it. These splines also themselves have much fewer parameters. So if I want to write down the spline, I can I choose, I don't know, 6 or 5 points on this curve, and then I'm fitting a spline through these 5 points, and then I'm moving around these points and the spline in order to get the function that I want. And these splines cannot overfit easily. So essentially, when you do a spline, you always get something like this. You cannot have these huge oscillations in between. So I don't need to put a million parameters in it in order to make sure that I'm on this tail end where the arrow is down. Just sort of using a spline with a few parameters will automatically give me something where the green curve is very low or very, yeah.
Okay. All right. Thank you.
Yeah, thank you for the questions. Yeah, please, I forgot to say this in the beginning. Please interrupt me if you have questions. I can't really see Zoom, so just shout out if you have questions.
Yeah, no, that's fine. I'm monitoring the chat, and I've actually said if anybody has questions, they can type, and I will let you know.
Great.
But so far, the only questions have been from the audience inside the room, and they've just butted in at will. So that's fine.
Yes,
Please
thank
continue.
you. Great. Yes,
Please
thank you.
continue.
So in your networks, the arrow goes like 1 over d, where d is the dimensionality of your input. For splines, the arrow just goes with 4, where 4 is sort of 3 plus 1 if you have a cubic spline. And we wanted to check this. So the first thing that we did is we took a neural network which learns the Bessel function in this case. So J0 of 20x. This is clearly a one-dimensional input. It just depends on x. And we trained sort of the cans, and we trained a collection of neural networks with different depths. And we saw that theoretically, we would expect them to follow this n to the minus 4 law for cans. In this specific case, since the input is one-dimensional, it should also follow this n to the minus 4 law for neural networks. And you see that sort of it tracks this curve quite well, the can. The neural networks also do initially, but then at some point sort of they flatten out and this scaling, I mean, this behavior breaks down, but initially they seem to be also following this n to the minus 4 curve here. Okay, so if your input is one-dimensional, sort of it doesn't really make a difference. But then sort of we took this function, which now is 100-dimensional, sort of it's just doing x of sine squared of pi x over 2. And in this case, if you have 100 inputs, so you know your alpha in the exponent is 1 over 100 or 4 over 100. So n is, so this arrow now goes down like n to the minus 0.04. So it's sort of, it's extremely flat here, and you would have to put tons and tons of parameters in order to get the arrow down. Whereas for cans, it's still n to the minus 4, and at least initially it follows this, it then also sort of stalls out. But you see the overall error is much lower for the can, and it's improving, at least initially as you go with the number of parameters, it's improving much better than the scaling law for the neural network tells you. Okay, so this is essentially the first part of my talk. If you want to try out cans, you can find them on the GitHub of the first author of the paper. So you can download it, play with it yourself. You can train them to your problem and see whether you can interpret what comes out and sort of throw some physics problem at it and see whether you can learn something by looking at this function, or perhaps just use its sort of better behavior and the scaling laws to get better results if you're not even interested in interpreting it. Okay, so that's the first part. You change the neural network architecture in order to make it more interpretable. The second part is, as I said, you don't try to interpret the neural network itself, but you try to interpret what the neural network does. And this is what we do in reinforcement learning. So let's say you have a binary classification problem. So somebody sort of shows you an image and asks, is this animal a cat?
We do have a question in the chat. It might be good to just address this question right now.
Yes.
Before moving forward. So
Yes,
do you want me to read out the question for you, or do you want to open
yes,
the
if
chat
you
for
could.
yourself?
Can you
So
read
the
it out?
question is, yes, I can do that. The question says, if I'm getting you right, we're using cubic splines to approximate functions. Why cubic? Why don't we use sinusoidal functions just as in Fourier series?
Okay, good. That's a very good question, and I get this often when I talk about this. And yeah, as I said, it's a very good question. So at this point, you could just say, okay, I have a set of basis functions, and I can choose whatever I like. I could choose, Bessel functions or Fourier decomposition sinusoidal functions, or I don't know, Hermite polynomials or whatever I like here. And this is correct, this statement. We just use splines because we have a nice approximation theory for them. But also they have another advantage that I haven't talked about here, and this is something that's called a catastrophic forgetting. So if you look at the paper, you can see a plot where sort of you train a neural network with some data, and then sort of let's say in the range from 0 to 1, and then afterwards you train it in the range from 1 to 2. And since these neural networks are essentially all connected here, you cannot really change the function locally. If I change the function from what it does between 1 to 2, it will necessarily also change what it does from 0 to 1. And this can lead to it forgetting what it already learned about the function between 0 and 1 as I adjust sort of what it does between 1 and 2. If you use splines, these have compact support. So they are just sort of supported between sort of each cubic spline just sort of goes between this and this interval, or this and this interval, and this and this interval, and outside of them, sort of they are all 0. So I just have a bunch of cubics that live between 2 points or maybe 3 points, and outside of them they are 0. This means you can adjust them locally. If you had a sign is completely delocalized again, and you don't have this localization, so you might run into the problem of catastrophic forgetting again. But I haven't actually sort of made this precise. It's just sort of a thing that I think would happen, but I never ran the experiment to actually see whether this is borne out in practice. So take this with a caveat, but at least that's my understanding for why catastrophic forgetting is not happening in cans. So yeah, thank you for the question. It's a very good question, and it touches on something that I sort of didn't want to discuss because of the lack of time. But so yeah, thank you for asking. So that gave me the opportunity to briefly talk about it.
I have one more question, please.
Yeah, two-part questions. First, it's still probabilistic, right? Because even when you sum those up, right, you're passing it through a nonlinear function, right? You're essentially, and like the second question is that how does it perform on the test data? Like, doesn't it suffer the CAN algorithm? Because it's, essentially the error goes down way too fast. So could there be a possibility for overfitting there? Like how
Thank
is
you
it
for the question.
Yeah.
Yeah. So the first question is, yes, absolutely. It's still probabilistic in the sense that functions that it learns here are randomly initialized. These spines are randomly initialized, and then you train it so it could find different functions. If you train it multiple times for this thing, you will always find it sort of converge to this. However, of course, this is just an empirical observation. This is not guarantee. But the nice thing is once you have this formula is not probabilistic anymore. There are no zero parameters in this formula. So this is just the output, and you can take this function and you can check it against the test set to see whether it's true, or you could sort of take it to be true and then ask what would it mean if my output actually depends on the input in this specific way. What would this mean for physics? What would be the implications for my physical model or so?
All right.
Yeah. Then secondly, what I'm plotting here is already the test loss. So this is how it performs on unseen data. You're absolutely right. It could overfit, but if this was the training loss, this wouldn't tell you anything about overfitting or not, but I'm plotting already sort of its behavior on the test cases.
All right. Thank you.
Yeah, thank you for the question. Okay, if there are no further questions, then I will go to the second part.
Yes, please continue.
Yeah, good. So yeah, so you want to ask it, is this animal a cat? What you do is you put it into your black box neural network, and it says sort of, I'm 97% sure it is a cat, and I'm 3% sure it's not a cat. And then you just go with the majority vote, and you say, okay, you tell the user, yes, that is a cat. And for cat images, that might be fine. But now let's sort of take this example. You give it a go board, and you ask, is there a winning strategy for white from this position? You can train a neural network, and it will say, I'm 91% sure there is, and I'm 8% sure there isn't. But this answer is completely useless to you. I mean, if it doesn't tell you sort of, as a white Go player, or even as a black Go player, if it doesn't, so it just tells you, yes, you can win, you cannot do anything with this information. And so in mathematics, you have a similar problem. If I ask it, is the Poincaré conjecture true or false? And it says I'm not 95% sure it's true, it is completely useless to a mathematician. Even if it said I'm 100% sure it's true, it would still be completely useless to a mathematician. So the question is sort of, how do we use that? How do we make this somewhat more usable, this classification task? And so one way is you can just ask a different question. You can just ask, what is the next best move for the white player in this position? And now sort of there's a 19 by 19 grid. So there are 361 possibilities, and it will just tell you sort of a probability. So there's some probability putting the stone here is the next best move. And you can just look at this, and then you ask it again. So if you do your move, you ask again, what is the next best move? It will tell you now, do this. You ask again, what is the next best move? It will tell you to do this. And in the end, if you won the game, you can just look at all the moves it told you to do, and you see that sort of, yes, there was a winning strategy for white because I just played it. That's the idea behind the reinforcement learning. So if you want to look at it this way, you have some combinatorically large search space. In Go, essentially, you have a number of possible Go boards. As I said, you have this 19 by 19 grid, and on each grid point, you can have a black stone, you can have a white stone, or you can have no stone. So that's 3 to the 361 possibilities. So that's 10 to the 270 or something. Sorry, 10 to 170. So that's ginormous. And the reason why nobody was beating Go with any classical algorithm was precisely this problem. If you try to sort of brute force this problem, you just start from this current Go board, and then you try all the 361 moves you can do, and then you try all the next moves and all the next moves. You would have to build the search tree with 10 to the 170 states in it, and of course that's ridiculous. The number of atoms in the universe is 10 to the 80. So if I stored one Go board on each atom in the universe, I still would be getting nowhere. Yeah. So this is not a way you can beat this problem. So what you do instead of trying to brute force this or to sort of search this tree is you train a neural network which just tells it what the next best move is. So instead of doing all the moves and searching all the possibilities, I just ask the neural network what is the next best move, or maybe what are the next 3 best moves. and I just follow these branches in the tree that the neural network suggested. And I'm doing this over and over. I just ask it now, what do I do? Now what do I do? And I continue. And if I reach sort of a winning position, then I can answer the binary classification problem. Is there a winning problem? Is there a winning strategy? I can answer this with yes, because I can just sort of look at all the moves that it proposed and see that this wins the game. That's the idea. So essentially, the setup for the algorithm is the following. We set up an algorithm that solves the yes instances of the decision problem. Does object O have property X? And the way we set it up is it should hold on the yes instances and it should produce a truth certificate. What I mean by this is if the answer to my problem is yes, it has this property, or yes, there exists a winning strategy, it should tell you yes, it has a winning strategy, but it should also tell you what the winning strategy is, and it tells you by just sort of telling you what type of moves to do in order to get there. And we don't make any assumptions about what happens if there is no winning strategy. So then, or if the answer to your question is no, then the algorithm can just run forever. Of course, in practice, it will do something very specific, but we're not making any assumptions about that. So we cannot decide negative answers. We can only decide positive answers with this. So if you can formulate a question where you care about whether the answer is yes, then you might be able to use this strategy in order to prove in a way that every mathematician would be satisfied that the answer is indeed yes, because you can just sort of show them the mathematical manipulations that you have to do to your object O in order to see that it has property X. Just like sort of showing the different go moves in order to win the game. So this is particularly good, as I said, for problems that have these combinatorically large search spaces. So you have some discrete set of moves, and the set of moves doesn't even have to be big. So for Go, as I said, it's 361. The problem is that the set of states is very big. So the different type of Go board configurations, that is 10 to the 170. That is what makes the problem so hard. And these type of combinatorically large discrete search or optimization problems, they are ubiquitous in physics. As soon as something is quantized, it's discrete. And so we apply this to a problem in string theory, to a number problem in string theory, and I will give this example in the very end. But yeah, it appears every time that you have quantized something in physics. And of course, it also appears in discrete mathematics. It's also very ubiquitous. You have topology where you count the number of holes in some space. Groups, representation theory, number theory, they all deal with discrete objects. And what this algorithm sort of does is it gives you a way of, if the answer is yes, it gives you a way of checking that the answer actually was yes. So this works very well for so-called NP problems. So these are problems where if somebody gives you the answer, you can very quickly check that it is indeed the answer. But finding the answers is very, very difficult. So finding the answers takes exponentially long, but checking that it is actually a solution is very fast. That's sort of the type of setup that you want, because the neural network will give you a solution, and then you can just verify it quickly that it actually is a solution. The neural network is not lying to you. Okay, so let's illustrate this in one example, which is string theory. I won't introduce string theory in 9 minutes that I have left in my talk. All I want to say is sort of it's a model for the universe, for the 4 fundamental forces in nature, sort of the strong force, the weak force, the electromagnetic force, and gravity. It's combining all of them. And one of the predictions of string, so the way it does this is it makes the assumption that particles are not point-like, but they are stretched objects, one-dimensional stretched objects that are called strings. And this seems like a very simple replacement, but it has very, very deep implications. And so one of the implications, or one of the predictions of, well, something that's called critical superstring theory, is that the universe is 10-dimensional. And then you look around and you say, okay, I only see 4 dimensions, where are the other 6? And the way that you can make contact with the experiment is if you postulate that the extra 6 dimensions that are predicted by string theory are there, but they're very, very small. They are small enough that we can't detect them in experiments yet, but they are small enough so that the string sees all 10 dimensions. So both are happy, okay? That's the idea of string theory. And the way then you get particle physics, let's say, out of this is you take your 10-dimensional space and you put objects into this 10-dimensional space on which strings, which you can think of as just sort of stretched rubber bands, where you sort of suspend these stretched rubber bands between, and these are what are called branes. So I have my 10-dimensional space, which I assume is a 4-dimensional space plus a small 6-dimensional space, some compact 6-dimensional space, and for the strings of constraints, this critical superstring constraints these to be so-called Calabi-Yau manifolds. So they are very special manifolds with properties, and inside of these extra 6 dimensions, now you have sort of suspended strings that sit between what are called branes. Okay, so this is essentially the setup that we have. And now the question becomes, in order to get out the particle physics that we observe and the cosmology and all of these things, you have to tell me how many of these branes do I have, so how many different planes do I have between which strings are suspended, and where exactly in these 6 dimensions are they living. So if you assume our 6 dimensions just have the shape of 3 two-tori with some discrete action to make it feasible, you could parameterize the position of these branes between which the strings are suspended in terms of 6 numbers, which essentially tell you how often they wind around the A cycle and the B cycle of each of these torus. Yeah, so for each of these tori, I could say, so if it winds around 1 times this and 0 times this. For the second torus, it winds around 0 times this and 1 times this. And for the third torus, it winds around, as it goes around 2 times this, it goes around 3 times the other cycle. So I just give it 6 integers, sort of n1, n2, n3, and m1, m2, m3. This tells me now where these branes sit between which I suspend the strings. And then I can tell you how many of these branes do I have sitting on top of each other. This is this number n. And I can do this, I can put as many of these brane stacks into my Calabi-Yau as I like. So I can put up to as many in there, which now means that the physical problem that I have to solve depends on 7 S parameters. So what I now do is I assume that I have these S brane stacks somehow in my compact 6-dimensional space, and I solve the equations of motion that string theory gives me. And since this is a quantum theory, it's quantized, these numbers here have to be integers. I cannot sort of wrap this half a times or square root of pi times. This has to be integers. The number of branes that I have are integers. So everything is an integer here, which means I'm dealing with a number theory problem more precisely with a Diophantine equation in 7S parameters. And I can formulate the consistency conditions in terms of these 7S parameters. And I've written them down. There are 3 different types of consistency conditions that come from the equation of motion and from some mathematical constraint called K-theory. But the important thing is I can write down these 3 conditions. I just call them condition 1, condition 2, and condition 3, and they are just Diophantine equations in these parameters, n's, m's, and so on. And now what I do is I set up a reinforcement learning algorithm. I want to know whether this set of Diophantine equations has a solution. So what I do is I set up a reinforcement learning algorithm, which just sort of traverses this huge state space, so that it sort of tries out different n's and m's until it found a solution to all of these questions, in which case the answer would be yes, there exists a solution, and it could show me what the solution is. That is the idea of how we want to use reinforcement learning to solve the string theory problem. So we set up our algorithm, we train it for a while, and it does this. So first, it just solves, the first condition is the thing it solves first. Once it has found solutions to condition 1, it starts to solve condition 2. And once it has solved condition 1 and 2, it starts to solve condition 3. And it's not clear that a priori, it's not clear that you can even do this. These are coupled Diophantine equations. So these n's appear in all three equations. So it's not clear that I can actually sort of solve 3 without destroying a solution to what I had for 1 and 2. But string theorists looked at this 10 years ago, and they found out a way of decoupling condition 3 from condition 1 and 2. So what they did is they brute forced solutions to 1 and 2, and once they had this, they could solve condition 3 without destroying the solution to condition 1 and 2. So it's a bit like if you solve a Rubik's Cube, you just sort of play around with it until you have 2 phases solved, and then there is an algorithm for how you can sort of get the other phases solved without destroying the solution to the first 2 phases. And when we then looked at, so this is a known strategy. What you have to do, you have to add so-called brains that are of C-type that will allow you to sort of solve this equation without destroying the solution that you already found for condition 1 and 2. And when we then looked at what the neural network was doing, it was also employing this very same strategy. So it was, as it started to solve these problems, it started to employ more and more of these C-type brains. So once it figured out how to solve it, it was employing 80% of C-type brains, whereas sort of statistically you would expect to have something around 20% of C-type brains. So it rediscovered this human strategy of decoupling equation condition 3 from condition 1 and 2. But then you can sort of let it train longer, and what it did then is it solved condition 3 first, then it solved condition 1, and then it solved condition 2. And this strategy of solving the problem is much more efficient than sort of solving 1, 2, and then 3. So doing it this way is better somehow in the sense that you find more different models faster. However, if you look at this, there's no way known to humans how you can solve condition 2 without destroying a solution to condition 1 and 3. So you can decouple 3 from 1 and 2. There's no known way of decoupling 2 from 1 and 3. So it rediscovered this human strategy, but then it found a better one that humans hadn't discovered yet. Yes, so that's the example that I want to present for reinforcement learning. So my time is also up. I'm exactly at 1 hour, so let me just conclude. I discussed 2 ways in which you can use tools from modern machine learning in order to make it applicable to theoretical physics and mathematics. One was to rethink neural network architectures and use scans which are more human interpretable and better suited for interpretation and for symbolic regression. And the other was to use reinforcement learning to solve this decision problem by sort of finding trajectories through state space that give you a truth certificate for the yes instances of your decision problem. And I showed you how to solve a number theory problem in string theory using this. And we have applied this to many other problems in mostly low-dimensional topology, so not theory, recently. Okay, that's all I wanted to say. Thank you very much, and I'm happy to take more questions.
All right, thank you very much. Right, so do we have any more questions?
I have a question.
Yeah, go ahead.
So this is about the GANs portion of your talk. I was just wondering if you could talk a bit more about how to get a symbolic expression out of once the training is complete for the network, because you talked about the complex function, right, with like 100 parameters or so. And what I'm wondering is, like, for a parameter like that, as training, like, is the symbolic expression something you can extract you can stop training at a step and say, right now, this is what the symbolic expression is? Or is it something that you need to go in afterwards and interpret out of, like, once you're done with the training? I guess I'm just confused about how exactly the symbolic expression is derived from this.
Yeah, so in this case, what we're doing is we're literally looking at this and we say, okay, so if this looks like a parabola, so you can fit a function that's ax squared plus bx plus c to this function, and you would find that it's just x squared. You could take the spline here and fit a function a prime x plus b prime, a prime x squared plus b prime x plus c prime to it, and you would find, again, it's x squared and so on. Then you could try to fit a function a times sine x plus b or sine cx plus d to it, and you would find that the answer is just sine x. And then you could try to fit a function c times e to the bx to it, and you would find that the answer is just e to the x. And then you get this expression out.
Okay. So is it sort of like, I guess is there a way to automate this process? Because
Yes, very good.
in the first step you're fitting it to a polynomial, but even in the, I know this is a much smaller number of parameters, but if I remember the plot correctly, I think even for when you were fitting that function with like 100, that complex function, I think you had on the order of 100 parameters, right? So doing it by observation might be tricky for something like that. Yeah.
Yes, it's a very good question, and this is actually a paper that I published very recently with a colleague from MIT and a colleague from Northeastern, where we precisely use these scans and automate this regression, this symbolic regression problem. So what we do there is essentially we literally take these images of these graphs of the functions, each one of them, and we send it off to ChatGPT and we ask it, what is this function? And we say, well, to me, this could be maybe x squared, could be x to the 4. So we take its answers and then we take its answer, if it says it's x4, x to the 4, we fit a polynomial a times x to the 4 plus b times x cubed plus c times x squared plus d times x plus e. We fit this to this function, and we do this for all functions that it proposed, and then we rank them according to how well the spline fits the proposal by ChatGPT. And then so we give it a score, and then we we take the best one, we tell ChatGPT, okay, we have this image, we have this ansatz, which works kind of okay. Can you make a better ansatz for this function? And we'll come back, so it will improve its own ansatz. And then you keep iterating this for a few times until it has given you a rather sophisticated ansatz that works good enough for your purposes, or you don't want to play this game anymore. And then you do this with each of the functions. And now ChatGPT has given you ansatz that you have then fitted exactly with coefficients to get these functions. Then all you have to do is you have to stitch them together according to the graph that the can learned. Then you get a more complicated expression, and this more complicated expression then you can simplify doing usual symbolic simplification, for example, using Mathematica or using SymPy, or you could also just send it off to ChatGPT again and ask it, I have this complicated expression simplified for me. And so running this, essentially just outsourcing the problem of fitting these functions to ChatGPT and to Python or Mathematica is what this other paper was about. And again, you can find the code on the GitHub of my collaborator, Thomas Harvey.
All right, thank you.
Yeah, thank you for the question.
Right. Do we have more questions? Any questions from the online audience? If so, please just unmute yourself and go.
Is there a gradient vanishing problem here? During
It's also a good question. So if you make it too deep, usually you have the problem of vanishing or exploding gradients. So in this case, what we could even do is well, you can still have an exploding gradient, but so what we could do in this case is, because it has so few parameters, it only has 100 or so, you can actually train with second order methods. So you can train with something that is not just based on a gradient, but also on the curvature. And so this is robust against vanishing gradients if you have more curvature information in there. So second order optimizers work here as well.
Okay, all right. Thank you.
All right, so last chance to ask a question. Online audience or people sitting here.
Yeah, I have a question.
Mhm.
So what kind of problems do we use scans for? So uh, is that a universal algorithm that we can use, or do you think that there are certain realms that scans do not really work well in?
I mean, it's a good question. People have used cans nowadays for all sorts of things. They've done can formers and convolutional networks with cans. They've used it for essentially everything that people have used neural networks for. There's this trade-off, sort of, as you see, the arrow goes down much faster, it goes down deeper. Of course, there's also a problem with, I mean, there's no free lunch here. Cans are slower to train. So they are not sort of the reason why neural networks are so fast is because it's just essentially just matrix multiplication, and NVIDIA has developed very good chips that can do this very, very quickly. Cans are not sort of, they're fitting splines. This is not some matrix multiplication problem. And so training them is much slower, but it converges also for much fewer parameters. So there's this trade-off between sort of training slower, but also needing fewer parameters, and you need to see which one works better for your specific example. I don't have a sort of one answer fits it all here. I think you just have to try out and see whether it works if you just want to get good results. So as I said, if you want some interpretable results, I would always try a can, because then you can get a symbolic formula out of it. And so I recently used can, for example, in mathematics. So there was a problem in representation theory of the symmetric group. I did it with a mathematician at University of Connecticut, Hugh Lee. And so they had the question of whether, sort of given the Kronecker coefficients, which are sort of exponential coefficients in the irreducible representations of the symmetric group, which ones of these are vanishing. And we used cans to sort of find a new a new sufficient criterion for when they are vanishing, and we were able to do this because they were interpretable, the cans.
I have another question. Please correct me if I'm wrong. Does this method expand our domain of analytic solutions to problems, right? So, for example, you
that's the
have
hope. That's the
yeah,
hope, yes.
yeah, okay.
Yeah, exactly. So the hope is sort of there's some unknown law that's governing, or some unknown map between two physical quantities or two mathematical quantities that is as of now undiscovered. And now what you can do is you can just train a neural network to map sort of quantity A to quantity B. And there's an example of this where we did this in knot theory in the Can paper. So what we did there is essentially we just had this in knot theory, you have sort of algebraic invariance and geometric invariance, one coming just from thinking of the knot as a geometric object. The other one comes from it thinking about it as an sort of as an algebraic instance. And
Okay.
low dimension topologists really sort of, there are these two different worlds of geometry, and people don't really know how to map up sort of quantities from one side to quantities on the other side. So now what you can do is you can just train a can, or even just a neural network in this case, trying to map sort of the geometric quantities to the algebraic quantity. And if the neural network succeeds, or if the can succeeds, this tells you there has to be some relation between these two. There has to be a map that sort of relates these two. And knowing that there exists this map, then mathematicians can go in and try to prove the existence of this map, or what this map actually is. And so people did this with neural networks in the past. This is a Nature paper by Google DeepMind, who did this together with knot theorists in Oxford. But so if you do it with a can, sort of, so what they knew, they just knew there was a relation, and then they sat down and worked hard in order to figure out what this relation was. If you do it with a can, it will also tell you there's a relation, but it will also sort of tell you the functional form of this relation. So you might already have a better starting point for how you prove this relation.
Yeah, that's really interesting. Thank you. Thank you.
Yeah.
Right. Any other questions? Well, I guess it's time to conclude. Thank you very much, Fabian, for taking time out of your busy schedule for us. It was wonderful to have you over.
Yeah,
And
thank you very much for
perhaps at some
your
point you can come here physically as well.
would be great, yes. Yeah, thank you for
Thank
staying
you.
around so long, so late. I know it's late in Pakistan, so thank you for staying around so
Well,
long.
the great thing about staying late is that we can now just get up, have dinner, and go to bed.
Okay, great. Yeah, I have my day ahead of me.
Yeah.
All right.
So have a good
Thank
day.
you.
Bye-bye.
You too. Bye.
Bye.